Hey gang, welcome to 10.08 Intro to Action Potential. So what we're going to do in this is we're going to take an overview of nerve impulse transmission, which is called action potential. And we flipped back a couple of pages. This is the bottom of the page that says you are a battery. We're going to talk about what that means a little bit more. It's got the water tank and the pump there on the top as well. So we talked about the fact in the last video that the sodium potassium pump keeps a voltage at rest, so resting state of negative 70. And why millivolts? Well, a 9-volt battery has a lot of usually like copper, nickel, or and cadmium in it. And we're talking about a big amount. A neuron is a very, very small structure. You have to look at a microscope to see. So we have, instead of volts, we have millivolts. But, and don't let the negative confuse you. So if I could come in and I'm going to draw a neuron. Looks a little bit more like a Dr. Seuss. There's my nucleus. What this means is that outside the cell is, now we say the outside is positive to the inside of the cell, and you might be a little confused because you're like, well, and then the inside is going to be negative, and this is going to have negative 70 millivolts. Because when we measure it, it's actually 0 to negative 70. But again, voltage measurement's a little bit relative, but compared from the inside to the outside, this is positive and this is negative. And you'll see if you look ahead, let me grab one of your sheets ahead. So I'm just going to show you this quickly. You'll notice here it says at rest, everything outside is positive and everything inside is negative. So that's the convention. And this resting state is maintained. This is kind of orange, so I'm going to pick orange. This is maintained by the sodium potassium pump. Protein actively pumping sodium outside the cell against the concentration gradient, which means we're making it more concentrated. So if I could take a slice, let's say I'm taking a slice. I'm going to take this slice right here, and I'm going to do it in cross section. So I'm going to look at this axon. Instead of looking at it from the side, I'm going to slice it. So here's a cross section of my axon. And what we see is that inside the axon is negative 70 millivolts. So we've got negative, 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 positive, 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 positive. And we used a lot of ATP. So actually, not just a little bit of ATP, your body makes ATP through cellular respiration. And for every 10 ATP you make, 6 of them get used to create this voltage. That's how important this is. So 60% of the ATP you make goes to setting your voltages across your axons in nerve cells. Well, it's a little bit like, again, the reason this is on this page, I'm going to go ahead and wing up. We created a potential difference. So in our example up here, we took water and we pumped it up, and now we can drop that water. Remember, we had a water wheel, and we can do work. In the same way, by pumping sodium ions out of the cell and creating this potential, we now can open, if we open up a channel in this axon, all of a sudden, remember, it hates not having things equal. All of this charge is going to flow into the cell just like the water flows the water flows down to the ground. It's the exact same type of scenario, only we're using electrical charge instead of water. And so that's what happens. So from here to here, and we go to green next, it says depolarizing. So in green, in this depolarizing phase, what happens is we open voltage gated channels, voltage gated ion channels. And that's why we went over in 2 videos ago, voltage gated ion channels, ligand gated ion channels, and mechanical gated ion channels. So we to change one spot. And what'll happen is it's going to spread, as we'll see later, but we get that voltage gated ion channel to open. And because there's a difference here, the positive ions are going to rush into the inside of the cell. And they're going to rush, and they're going to rush, and they're going to rush, and they're going to rush. And we're going to add, so we've got all this positive charge rushing in. And it changes the voltage to positive 30 millivolts. Well, think about it. If you're down here at negative 70, so here we go. We've got ions rushing in, positive, 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 positive. It's going to take us up to positive 30 millivolts. So this was like a charged battery. What we had here to start with was like a charged battery, charged by the sodium potassium pump. Here we have a dead battery. So now we've used that charge to help us. And what we're going to see is this actually sends the signal later. Don't worry about that right now. So we've got our charged battery. We're at resting state. All of a sudden, those gates open. Here come my sodium ions. Now I have a dead battery charged. And the process of discharging the battery, of discharging this charge, is called depolarizing. Well, if you have a rechargeable battery at home, or if you use your phone, you know, if your battery dies, you have to recharge it, you have to plug it in. And that's what happens here. And this whole process is the process of recharging the battery. So we have, and this is going to be in purple. So let's do one more cross section. By the way, over here, now I'm positive on the inside. So through a series of other, so the next steps, we have some other gates that open, some other channels that open, and the sodium potassium pump. We get the positive, then it'll flow back out. And then the sodium potassium pump finishes it. So we get the positive charges flowing back out. And that takes us back to the beginning. Actually, what happens is, so if we're repolarizing, we get another rush, we get ions flowing out, flowing out, flowing out, and we go too far. We go down here to negative 90 millivolts. So we actually get further than we need to be. So what gets us back to that starting negative 70? The sodium potassium pump. And that takes us back to the beginning. So what I want you to understand, though, is that this repolarizing phase is like the recharge. Now, don't get bogged down in the details. We're going to handle the details in 10:09. Again, what I want you to see is the big picture here. So the caption up above says you are like a battery, and you are, every neuron in your, a better way to say it is every neuron in your body is like a battery. It's sitting there and it's got a charge, just like the ends of a 9-volt battery. You've got a positive, if you look at a battery, one side's positive, one side's negative, and you have a total voltage across the two terminals. So here on your charged neuron that was charged by the sodium potassium pump, you've got positive outside, negative inside. We open up some channels, and because there's a difference, all of a sudden you get this rush into the axon, and it flips the voltage from negative 70 to positive 30. Now we've used that, it's done. Now we have to recharge it, and to do that, we open up some more gates, and we get a flow back in. It goes too far, it has to get fixed by the sodium potassium pump. But the takeaway here, the big takeaway is that we create a charge, we use the charge, we recharge the cell. And that is how your neurons work. What's going to happen is this is going to happen at one spot. This spot's going to trigger the next spot. That's going to trigger the next spot. And you'll get an electrical flow down the entire length of the axon, which we're going to talk about in, so in 1009, we're going to go through the details of how this charge gets set, used up, and reset. And then in 1010, we're going to look at how it moves down the entire length of the axon, which is called propagation. Okay, that does it for our intro. On to 1009.